my current argument only works if the length of y is 1. So like technically speaking, he's got like y over c is equal to this, where c is the length of the vector. If you divide by c, then this makes this a unit vector, so star is a reasonable equation then. But that makes a, like a 1 over c here, and it puts a over c here as well. But with that adjustment, this argument works. And then you can just multiply through by c, and you get back what we wanted. All right? All right, now at this point, now is exactly the time I need to get the projector out. Where am I? Here it goes. Because I'm about to, okay, so like the next thing we're going to define is what does it mean for the acceleration to be 0 for a curve? What kind of curve is that?
Straight line or a parabola?
A straight line or a parabola?
The velocity would be a straight line, right? For it to be 0, or it have to be.
Yeah, well, that, interesting. So you say that, so for if the acceleration is 0, the velocity must be a straight line. Like that's a.
No, well, I'm talking in 2D.
Well, we are in 2D, intrinsically.
So if the acceleration is 0.
I mean, I like what you said. It's a straight line. I mean, that's the right intuition for that. But what do we call that? What do we call a straight line on a surface?
I mean, it's still going to be a function.
I mean, in the case of a plane,
It's a straight line.
the straight line
On the surface, it could be curved.
could be curved, right? The straight lines, quote unquote, straight lines on a surface.
You're looking down at it, like, or in my.
These are.
If you have a surface, well, if you look straight down at it, it's going to be a 2D plane, which is going to look straight. Once you pop it up in a 3D, it's going to be a curve.
Mm-hmm.
You're saying we can differentiate that curve?
What I'm saying is that the covariant, the acceleration of a curve being 0 on a surface makes that curve what's called a geodesic.
Oh, yeah, that makes sense. So
Right.
You can take a P and Q, and that would be the shortest line there.
Mm-hmm. Yeah, we haven't proved that, but yeah. Let's see here.
That makes sense.
So we're nearing the end of lecture 25. The equations to describe geodesics are rather complicated, and I only scratched the surface of them in here. It's a concept which we sort of bump up against as we're talking about the Gauss-Bonnet theorem today. But so it's like, okay, well, the other thing is to really, I mean, to be honest, to really calculate geodesics, we need to be able to solve some pretty nasty differential equations, right? But have you had differential equations? You have. Yeah, you have?
I'm in it.
You're in it.
Just finished. We were solving an issue value problem. We're doing. Oh, we were saying that like you could do things with a Laplace transformation. Then we, and you can. Oh, and if you can take another thing and convert it over to a thing. To get what you want.
Take a thing and go to the thing.
Yeah. Essentially, we took a function w of t that is in radians.
Mm-hmm.
Convert it over to y of t, so we can convert it to prime. Or we can convert it back and did the normal Laplace of that. And
Mm-hmm.
we converted it back into w.
Hmm.
T. Solve the initial value problem where w prime of t minus 2 w.
Oh, you're saying you solved initial value problems with Laplace transforms?
Yeah.
Ah, cool.
But we converted it to y of t.
Let's see if this. I'm trying to find the right setting for this to show up best. Why is that so tiny?
You can just
Yeah. Is that better for you? Yeah, there we go.
But yeah, we're still on the plus. I don't know how many chapters this book has. More chapter 7.
Chapter what?
7.
Chapter 7.
But yeah, we're still on the plus transformations. Is there more differential equations, like first year or first?
Well, there's series methods.
Oh, yeah. Well, I did that in Cal 2. We've done that here.
Let's see if I can just remember where I'm getting to. I'm never happy with the zoom. I guess that's safest. That way I can see everything in the camera that I move. Uh-oh. Pesky. I'm trying to get the come on. Come on. Trying to get the power adapter to actually, it's got a short somewhere in here, and I have to fuss with it in order for it to not drain my battery. Sorry about this. Although, I guess it's just as well we're buying time for Maya. Not my intention, but I'll allow it, I guess. You see the red light?
Yeah.
When that flashes, it's like making contact. Come on. Oh, there we go. I got it. Okay. We got it. You have not missed a thing. That was just me setting up the camera since you left. All right, so let me get my laser. Oh. Yeah, I guess that one. All right, so we've defined our covariant derivative along a curve, right? We have just gone through lemma 3.4. All right. And just, we were laboring the technical details of the proof, but we should stop and think about what this is saying intuitively, right? It's saying that if you have a vector field of constant length along a curve, the vector field can only change direction, but the only place it can change direction into is the orthogonal direction to the given the orthogonal direction to y, which is jy. So, and then the mechanics of that comes also from two things. For one, from the change of the angle function along the curve, which makes perfect sense, right? If you think about, well, of course, right? As the angle between y and e1 changes, then the derivative of y should change accordingly. But it also comes from the rotation, the connection coefficients of the frame, the omega 1, 2 of alpha prime. So, all right. So there's that. So that brings us to a definition. A vector field V along a curve alpha in a geometric surface is parallel, provided V prime is equal to 0. And V prime is the covariant derivative, right? And then I launch into this calculation on page 24, right? And the theorem that I'm proving in the purple is the following, which is that the theorem I'm proving here is if the vector field is parallel along a curve, that means the length of the vector field is constant along the curve. All right? Again, parallel implies constant length. And I gave proof in purple here, which is somewhat lengthy. See, I'm just going through the definition. I'm like, well, v prime is this and that, right? And since these are both, E1 and E2 are linearly independent, that means for this to be 0, the coefficients must both vanish. And so that gives me two differential equations in F1 and F2, namely this one and that one. And, but I also know that the length of v squared is F1 squared plus F2 squared, which is, you know, differentiated to give me 2f1 df1 dt plus 2f2 df2 dt, which then if I plug in these differential equations up here into my derivative of the length squared, I get 0. Therefore, the length squared is constant, which means the length is constant. So that was my proof of this. Would you like to see O'Neill's proof?
Sure.
Here it is. So to prove that the it's kind of depressing. To prove that the length is constant, he just says, okay, well, look at the derivative of the inner product of v with v. But then by properties, well, this is a property of the derivative of the inner product is this, it's got this product rule, v prime v with plus v with v prime, which is twice v prime with v, but v prime is given to be 0, so 0 with v is 0, so it's 0. I mean, I think this is okay, but I mean, technically speaking, we should really have a homework problem to prove the first line here in O'Neill's derivation, right? I think my proof in purple is good, but I always like O'Neill's arguments, you know? Okay, anyway, moral of story, parallel vector field, constant length, right? Okay. This is page 24 of lecture 25, which is not really page 24 of lecture 25, it's page, I don't know. Okay. All right, so let alpha be a curve in a geometric surface and v a tangent vector such that, you know, P, and we're giving P to be the point alpha of T naught, claim there exists a unique parallel vector field V such that when you plug in, I should really not have V of T naught there. That should be V of alpha of T naught, or V of P is V, I think, there. Anyway, here's the proof. So we're trying to solve V prime of T equal to 0 for all T. And so my initial thoughts are, well, if you look at this, it gives a differential equation. You have initial condition, so by the existence and uniqueness theorem of differential equations, you have a solution. But O'Neill gives a better argument. Here it is. So since, all right, so V is parallel, right? We know it has constant length. So that means that there exists a constant C such that V is cosine phi E1 plus C times sine phi E2. Does that make sense to you guys? So like the point is E1 and E2 are always there at each point in the tangent space to build vectors from. So if you know the sort of standard angle with respect to the E1, E2 frame, which we're calling phi, you can build the vector from the E1 and E2 components by that formula there, right? And then the C is just the magnitude. So there's the formula. Now, but we also know that V prime is 0, right? So V prime being 0 implies that phi prime plus omega 1 to alpha prime must be 0 because of the definition of covariant derivative, right? And, oh, also by lemma 3.5, which was that jy thing, right? So we have phi prime of omega 1 to alpha prime equals 0. Let's see here. So then I just integrate this equation here, right? You can solve that for d phi dt equals to minus omega 1 2 alpha prime. Integrate both sides and you get the formula down here. Phi of t is equal to phi of naught minus the integral from t naught to t of omega 1 2 alpha prime. Du is a dummy variable of integration. right? Because we're using t to be a fixed but arbitrary time here. So there's the proof that, there exists a unique parallel vector field. And so how do you construct that parallel vector field? By specifying the angle function like so. So just to try to show you what I mean. So, ow. So think about this. When t equals to t naught, this integral piece drops out, right? And you're just left back with phi of t naught again. And so like initially, the initial vector is given by c cosine phi naught e1 plus c sine phi naught e2. So like that reproduces that reproduces the original vector that you're given at that initial angle. And then you evolve the angle according to this formula in order to match, in order to parallel transport the initial vector v into this vector field v. So the point is here we're given an initial vector and then we've got some curve, you know, and this tells us how to choose the angle to move that vector in such a way that it's always parallel, in the sense that v prime, the covariant derivative of the vector field that you're creating, is 0 along the curve. Which means that the vector field which we're creating has constant length, among other things, right? Because we just proved a parallel vector field has constant length. Now, so definition, v of t generated by this technique I just outlined is called the parallel translate of the vector v along alpha, all right? And so we do parallel translation all the time in Euclidean space. We don't even think twice about it, right? How's it go?
Is that the
Like,
question again? Sorry.
how do we do parallel translation in like Euclidean space?
You just take a line and plus or minus, or just do things to
Right. Let's talk about like a horizontal line along this.
Are you talking about algebraically or geometrically? How we translate?
Geometrically. So like let's take a horizontal line across the board here, right?
Yeah.
In physics, I say stuff like, you know, you've got a vector, and the vector, whether you put the vector here or whether you put the vector over here, it's the same vector, right? If we're thinking about my arm being the vector,
Yeah.
right? So what are we saying? We're saying that with respect to the curve we're parallel translating, the angle of inclination is the same here as it is here, right? That's because we're working in Euclidean geometry, where there is the connection coefficients are just 0. There's no rotating according to the frame rotating, because the coordinate curves with which you're doing the parallel translation with respect to, well, they're just straight lines. There's no bending of them. There's no curvature, if you will, and there's no curving of the frame. There's just what we call I hat and J hat and K hat in physics, right? So parallel translation in physics is easy, right? Parallel translation along a surface, you have to take account for the connection coefficients. It tells you how to bend and change the inclination angle to do this parallel translating. But if you have a curve that connects one point to another on a surface, and you know, you can calculate your connection coefficients, you can then describe you can parallel translate a given vector to another at the end, right? And if your curve goes all the way around, you could parallel translate the vector from one side back around. And the interesting thing is, when you get back around, you won't necessarily end up with the same vector you started with. They'll be different by an angle. And that angle is what we call holonomy. The holonomy. So here's a picture, a sad picture, but a picture nonetheless. You can imagine taking initial vector v, all right, and you parallel translate that vector along the curve alpha. You get to this one, right? Then you take that same vector and you parallel translate along this vector b. You get to this vector. But the parallel translate along alpha and the parallel translate along beta, they don't have to be equal. But because they're two vectors in a two-dimensional space, there has to be an angle which rotates one to the other. That angle is called the holonomy. Well, I think that's not quite right. Holonomy refers back to loops. So, but holonomy captures the non-triviality of parallel transport. So, what I'm just saying, like if you parallel translate a vector along one curve or another, you get a different result. Would we say that in physics? No, we say the exact opposite in physics, right? In physics, three-dimensional physics, we take great pains to tell students, you take the vector, you can put it here, you can put it there, you can put it anywhere. It doesn't matter how you do it, right? If you do it like here, then here, then here, or if you do, just straight to there, we're still ending up with the same vector. There's no concept of holonomy in physics because the angle that you get from parallel translating, there's no distinction. But on a curved surface, how you parallel translate, if you parallel translate around a loop, then the curvature of the underlying space will be detected by that rotation of the vector field along the parallel translate. So.
That makes sense because if you take a paper and then bend it, if you were to take that same vector, it would not have the same angle for relation to like what the curve was on that.
Right. So this example 3.7 goes through the calculation of a holonomy around a sphere of radius r, and it works out to minus 2 pi sine of v naught. So the holonomy angle is 0 if you're at v naught equal to 0, which that would be like the equatorial circle. Otherwise, you get some holonomy angle if you parallel translate a vector around a sphere. And I will just point you guys, there's a picture in O'Neill that you got to look at for this. I really should have tried to transcribe that picture into my notes if I was, I must have tried and not liked what I got. But the picture's on page 344. Yeah. Let's see if I can do it justice. This, uh-oh. Yeah, I don't know I think it's going to be too fuzzy. I tried. Whoa! Extreme close-up. But yeah, you can see there, it's figure 7.5. So he pictures the loop, see that?
Yeah,
and as you can imagine, the vector, we can translate it around.
Yeah. But yeah, then that way you can keep it.
When it comes back, it's not where it started.
Wait, when it comes back, it's not where it started?
The vector parallel translates to a different vector, yeah.
How many loops around
Just once.
I know, but how many loops would it take to get back to the original?
Well, I suppose that depends on what sine of v naught is. I guess if sine of v naught is, a half, I guess it would take 2, right? If sine of v naught is a half, the first time you get minus pi angle between, so it's like made it go exactly backwards where it was, right?
Yeah.
And if you go another loop around at that latitude, is it?
Latitude
Yeah.
flat.
Yeah. Okay, so that's holonomy. And then finally, lemma 3.8, it compares the covariant derivative in 3 dimensions with the covariant derivative in the surface that we've been talking about the last hour or so. And this is the connection, this is the explicit formula which shows you the connection between the intrinsic covariant derivative that's defined on a surface in R3, the shape operator on that same surface in R3, the unit normal on that surface in R3, and the covariant derivative, which I taught you guys first before any of this, right? So there it is. That's how these things are interrelated. And I think that's a good place for us to stop. We'll pick back up next time here after a short break with lecture 26, which will straight away lead us to the Gauss-Bonnet theorem. What's that? Yeah, you can turn the light on for a minute.